Is this a 4 or is it? My neural network thinks there's a 0.4% that it's actually a 9. But here's the insane part. I built this entire brain from nothing but Rust code and raw mathematics. No TensorFlow, no PyTorch, no machine learning libraries whatsoever, just pure Rust and linear algebra. And by the end of this video, we'll have a machine that can look at your handwriting and somehow make sense of it. And we're going to build every single neuron, every weight, every gradient descent step ourselves. So let's build a brain. Let's start simple. A neuron takes inputs, multiplies each by a weight, adds them up with a bias, and spits out a result. This is just a weighted sum. The learning happens when we adjust these weights to get better outputs. But one neuron is like having a calculator that only does addition. It's not enough. We need more layers, more connections. Each neuron's output becomes input for the next layer. Now you might be thinking, that's a lot of individual calculations, and you're absolutely right. That's where linear algebra saves us. All these individual multiplications become one matrix operation. The dot product handles everything in one single operation. In Rust, this looks pretty clean once you get past the borrow checker. Here's the thing though. What we have so far is just a fancy linear function. Stack a million linear layers and you still get linear behavior. That's not very interesting. Enter ReLU, rectified linear unit. It's that simple. If the input's positive, pass it through. If it's negative, output 0. This tiny nonlinearity is what makes the neural networks actually powerful. Finally, we add Softmax to convert our network's raw output into probabilities. It takes any set of numbers and turns them into values that sum to 1, perfect for how confident I am that this is a cat versus a dog. To train our network, we need to measure how wrong we are. Cross-categorical entropy loss does exactly that. It gives us a number that gets smaller as our prediction gets better. Now comes the interesting part. We know how wrong we are, but we need to figure out which weights to blame and by how much. Think of it like this. Imagine you're adjusting the recipe for a cake. The cake tastes off, so you need to figure out, was it too much sugar, not enough flour, too much vanilla? Backpropagation does exactly this. It traces the error backwards through the network, calculating how each weight contributed to the final mistake. Then, we adjust each weight proportionally. Let's trace how data flows through our network. Its input, then linear transformation, then the activation functions, then linear transformation, and then output. So first of all, we're going to initialize the core structure of the network, which consists of two matrices to store the weights. One that connects the input layer with the hidden layer, and one that connects the hidden layer with the output layer. We'll be having two bias vectors, one for the hidden layer and the other for the output. Next, we will initialize the weights with random values just for the neurons to not learn identical features and to have a distinct gradient path during training. And for the bias vectors, they're going to be initialized to 0 because they can be adjusted freely during training. This line computes the pre-activation values for the hidden layer. Matrix multiplication, the w1.x, applies the learning weights to the input vector. The result is a vector that represents the weighted sums for each neuron. Adding the bias vector b1 shifts the activation threshold for each neuron independently. This linear transformation is the first step before applying the nonlinear activation function. The backward method computes gradients of the loss function with respect to all parameters. It implements the chain rule of calculus manually. A1 equals ReLU of Z1 and Z2 equals W2 times A1 plus the bias B2. This computes the gradient of the loss with respect to the output pre-activation values, which is Z2, and we do it again with respect to the second weighted matrix, which is W2. Now we do these with the hidden layer and the hidden pre-activations as well. Now the update method updates the network parameters in the direction opposed to the gradient. The learning rate, LR, scales the step size. Too large causes divergence, too small will hinder the learning speed. Each parameter is updated as parameter equals parameter minus the learning rate times the gradient, following gradient descent. And finally, we define the softmax function. That's it for our structure and its mathematical operations. Now we write some utility functions like the accuracy function. And finally, onto the main file. we load the MNIST CSV file, we parse its labels, normalize the grayscale values in the image, and then we store the labels in vectors, XS and YS, for later. And finally, the main function orchestrates the entire training and evaluation pipeline. It begins by loading the training and test datasets from the respective CSV files. A neural net instance is initialized with specified layer sizes, which is 748 for the input and 46 for the hidden and 10 for the output. Hyperparameters such as number of epochs, learning rate, and batch size are defined. Training then proceeds for a fixed number of epochs with loss and accuracy tracked per sample. After training, the module is evaluated on the test set. All operations are wrapped in a result type to propagate any possible errors.